Hello, today's class is virtual. A blank copy of the notes is posted on Learning Studio if you want to print them out and follow along. Entirely optional. The topic is Discrete Dynamical Systems, starting Chapter 4. And a discrete dynamical system is just a way of defining a sequence where the next term is some function of the previous term. So you've seen things like this before, certainly in discrete math and probably in calculus. Here's an example. The next term is some constant b times the previous one. So if I know a sub 0, I can use that to get a sub 1. Then I know a sub 1, I can use that to get a sub 2. A sub 2 generates a sub 3, and so on. Some of the most common forms will be linear, where it is just this form, or another slightly more general case, an affine dynamical system. A sub n plus 1 is b times a sub n plus another constant, m. And so let's look at an example coming from biology or ecology. Suppose a sub n is a biological population of deer, maybe in thousands. And it starts out at a sub 0, and then it's going to change. So n is going to represent time, as it usually does when we talk about dynamical systems. In this case, time in years. And from biology, we're told that the population increases by a birth rate factor times the previous year's population. It also decreases by a death rate factor times the previous year's population. That's natural death. And then the population decreases by a fixed number h each year. That represents a number of deers taken by hunters. So we want to write a dynamical system modeling this situation. So a sub n plus 1 equals number of deer next year is, well, first of all, it's a sub n, the number of deer in the previous year. And then we will add the number of newborns. So that's of the form r a sub n. So r is a birth rate factor, and then times the population gives this is the number of deer being born each year. Then some die, so minus d times a sub n. And then finally, some deer are killed by hunting, so like this. And now a sub n is common to the first three terms, so we might write this as quantity 1 plus r minus d times a sub n minus h. So a sub n plus 1 equals this quantity, and you see that is of the form of an affine relationship. So this whole expression can be identified with the b in the general form, and the negative h is m. All right, let's use an Excel spreadsheet to see what happens to this population over time. Let me attach my keyboard. And we will go to Excel, and here will be year and population. So the years are just going to start at 0 and increase by 1 each time. So I can make Excel fill out a number of rows. And the population starts at some value. Over here, I want to be able to change these values. So over here, let's have some we'll have an area where we can change constants that appear or parameters that appear. So a sub 0, the starting population, is something that I might want to work with, and the birth rate factor and the death rate factor and the hunting constant. So the actual values will go here. And I'll just put zeros there for now, and then we can change these. All right, so here in the initial population, I'm going to take this value. And then in successive populations, it will be the quantity 1 plus the R value. And I want this to be absolute addressing because I'm planning to drag this formula down. So the R value, and let's put dollar signs on that. Then minus the death rate. That's also absolute addressing. That gets multiplied times the previous year's population, which should be a relative address, and then finally minus the hunting parameter, which I want to be an absolute address, like this. Okay. And then drag this down. Of course, nothing is happening yet, but now we're ready to generate the population over time based on the values given in the worksheet. So they were that A sub 0 is 8, that R is 0.3, that D is 0.1, and that H is 1.7. And now finally let's generate a graph of the population as a function of time. Okay, so notice what happens. The population, deer population, is obviously decreasing over time. And in fact, this is n on the horizontal axis and a sub n on the vertical axis. By the time we get out to year 16, it looks like right here, the population has gone negative, which is biologically impossible. What has happened is the species has gone extinct, and the mathematical model just keeps going and generating negative values. But the proper interpretation would be the population declines, and then sometime in the 16th year, the population goes extinct. So let's record that. We have a sub n plus 1 equals, if I compute the b value, 1 plus 0.3 minus 0.1, turns out to be 1.2 a sub n minus 1.7, and we're starting out a sub 0 equals 8. And when we did this, we discovered that the population goes down, 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 and then mathematically goes negative. The next question says, okay, so we seem to be over-hunting the deer population, so let's reduce the number of hunting licenses available so that H is reduced to 1.3. So if I come here and do that, then you see that that made a huge difference. Now the population starts at 8 and increases over time. It looks like there's no stopping this, and in fact there isn't. So here, population would diverge to plus infinity. Species grows without bound. Next question, are there any equilibrium values of the system? So if this is the deer population, say in a national park, and you're the park manager in some sense, you don't like either one of these scenarios. You don't want the deer to die out, but neither do you want the deer population to go to infinity and crowd everything else out. So you would like to know if you can stabilize the population so that the population doesn't change year by year, or in other words, so that a sub n plus 1 equals a sub n. This is what we want. Well, let's come back here to this expression and note that if a sub n plus 1 equals a sub n, I'll just call that a bar, the bar meaning fixed point or equilibrium value, then that same thing happens here on the left-hand side of the equation and on the right-hand side of the equation. So I end up getting a bar equals 1 plus r minus d times a bar minus h. So notice the sub n is gone. I don't have to keep track of the year number anymore because I'm assuming that the population doesn't change from year to year. And that helps a lot because now we're trying to solve this equation for a bar, and it's easy. This is just a linear equation. So first of all, on the left and on the right, I have an a bar in each case. I can cancel those, and r minus d a bar minus h equals 0. So if we solve, we get a bar equals h divided by r minus d. So provided the population ever gets right to this point, then the population should stabilize. Let's see if we can find that on the spreadsheet. 1.7 was too large of a hunting constant. It drove the population extinct. 1.3 is not large enough. So how about 1.5? Okay, still growing, although not as rapidly. How about 1.6? And that seems to do it. Right there, the population has stabilized. So if you take and furthermore, the population has stabilized at 8 because that's where I started. So if you take those values, 8 and 1.6 and 0.3 and 0.1, you'll find out, in fact, that this equation works. So if I know any 3 of these variables, I can solve for the fourth. And so I could decide that I want to stabilize the population at, I don't know, something different, maybe 10. And then if I know r and d, I could adjust the hunting constant to make the population stabilize at that point. So supposedly we can stabilize the population, but question, does that really work in practice? So all measurements have some error in them, and this is population measured in thousands. So in fact, the starting population is not, I'm not going to be able to get exactly 8,000. Maybe it's going to be 7.99 or something. And so will the population still stabilize at 8 if I do this? And the answer is no. It is starting to go down, and if I carried this farther, I'd find out that the population went extinct. I just don't have quite enough deer to stabilize. And what if I have a little bit too many or more than that? Will it stabilize? And the answer is no, I'm going to grow, and I would keep growing toward infinity. what we've discovered is that if I draw another graph here, this is n, this is a sub n, and here's 8. This is my stable population or equilibrium value. So there are some scenarios. If I start right at 8, then I just get these horizontal dots. I stay at 8. But if I start a little bit below 8, then what happens is that we start going extinct. And if we start a little bit above 8, what happens is we grow without bound. So does the equilibrium value seem to be stable? That is, if I start near 8, do I stay near 8? And the answer is not at all. It's unstable. I can start very near 8 and still not stay close to 8. In fact, I get very far away from 8. So even though 8 is an equilibrium value, it's unstable, and that makes it not very useful in practice because again, there's little chance in real life that I'll be able to keep a quantity exactly on my target value. And if I'm off a little bit, then everything goes. Let's do one more thing, just kind of mathematical exercise. And that is, here's the general affine recurrence relation, and I want to guess a solution to that. So by solution, what do I mean? Notice that this is kind of clumsy for being able to tell what a sub 1000 is. What's the population in year 1000? Well, I have to do it by using A0 to get A1, and then A1 to get A2, A2 to get A3, A3 to get A4, and so on. I'd like to be able to have a formula in terms of n, where I could just feed in n equals 1000 and immediately crank out the population in year 1000. So let's see if we can guess a solution. And then I believe in a homework exercise, you're actually asked to verify that our guess is correct. We'll use the method of iteration. If you've had discrete math already, we talked about this. If you're in discrete math, we will talk about this. If you're not in discrete math and haven't been, don't worry about it so much. So let's generate A1. It's B times A0 plus M. Then let's use that to generate A2. It's B times A1 plus M. But now I'm going to substitute the expression for A1 into this second expression. So it's B times BA0 plus M, and then plus the other M. Let's do another. A3 is B times A2 plus M. And take this expression for A2 and put it here. And we get B times quantity BA0 plus M plus M plus M. So notice what we've done. Just as I said, take this and put it in the square brackets replacing A sub 2. Of course, we could keep doing this, but the goal is to recognize a pattern here. So let me come back here and do a little algebra on these expressions. Notice that if I multiplied everything out, there would only be one term that contained an A sub 0, and it is B squared A sub 0. Then there are two other terms, and they each contain a factor of m. Let me pull that factor of m out, and the remaining expression is b plus 1 times m. Do you agree with the algebra? Here's bm, that was here, bm, and then there's a 1m, and that was here, 1m. And if I do it down here, again, there's one term containing A0, it's B cubed A0. And then what's left over are 3 terms, all containing an m, so we'll factor them out. And what's times this m? Well, here's b times another b, so there's a b squared. What's times this m? Just this outside factor of b, so plus b when I factor out the m. And what's times this factor of m? Just a 1, like this. So now if you look at this expression and this expression and this expression, we can start to see a pattern, a very regular pattern. So my point is that I think I can now write down a sub n following this pattern. So first of all, there's a power of b times a sub 0. Which power of b? Well, when it's the second term, it's b squared. When it's the third term, it's b cubed. So when it's n, it's b to the n times a0 plus, and then what's happening in the parentheses is if I think about starting from the right, I'm adding 1 plus b squared and so on. How far up do I go? When it's the second term, I go up to b to the first power. When it's the third term, I go up to b to the second power, and so on. So when it is the nth term, I go up to the n minus first power. Plus dot dot dot. I can't write all of those terms. B to the first plus 1, and that's times m. Now notice that this is a solution in terms of n, but it's still a little clumsy because I still have to add all of these terms together. Here's a summation formula for a geometric series, and we'll use it. This is what I have. The terms are written in the opposite order. X here is b here, and capital N here is little n minus 1 here. So I'll recopy this term, and then if I apply the formula, it's b to the little n minus 1, but then plus 1. So b to the little n minus 1 divided by b minus 1 times m. And there we go. That's now what I was looking for. So a sub 0 and m are specific, and b, a sub 0, b, and m are all specific constants. And then you want to know what the population is 10,000 years from now. I just plug in n equals 10,000 and evaluate this expression. To match up with what you're going to work with in the textbook homework problem, I think they combine terms a little differently. So there are 2 b to the n expressions here. If we lump those 2 terms together, so multiply this expression out, and then lump the b to the n, the terms that have the b to the n factor together, what we have is b to the n times a0 plus m over b minus 1. And then there's another term which is minus m over b minus 1. This is where the textbook exercise has you start. Again, don't worry too much about that, but it is possible for simple dynamical systems to actually solve them analytically. Otherwise, we'll use our technique that we did with Excel spreadsheet. Let's discuss this idea of stability just a little more. So I'm not going to commit to a particular form. A sub n plus 1 is some function of a sub n. It might be a linear function or an affine function, but it could be something much more complicated. So a fixed point or an equilibrium solution is a value which, when you plug that value into the function, you get the same thing out. The function doesn't change this value a bar. And then we'll say that a fixed point is stable, and we sort of drew this picture before. Here's n, here is a bar, and we'll say the fixed point is stable if there is an epsilon. I can hear the groanings already. This sounds like limits in calculus. It's not really. So there's an epsilon so that if my starting value is within epsilon units of A, so here's an example. Here's a point that I can start. It's less than epsilon units from A. Then the sequence that's generated by this dynamical system will have limit A bar. So who knows what it does next, or next, or next, or next, but eventually it gets arbitrarily close to this limit value. And we saw in the deer population example, we saw a case where the 8,000 was stable. Then I changed the parameters a little bit and found out that 8,000 was not stable for that particular set of values of parameters. Let's work with the simplest dynamical system, just the purely linear one. And I want to show another way of checking whether a equilibrium solution or fixed point is stable. So first of all, what are the fixed points of this relation? I know I'm supposed to look at A bar equals B A bar. You might think of dividing out A bar. Don't do that. When you divide by variables, you can lose solutions. Let's instead get one side equal to 0. So I'll subtract, say, B A bar from both sides and factor out the A bar. A bar times 1 minus B equals 0. Now I'm specifically excluding the case when B equals 1, and therefore when this product equals 0, I know that A bar equals 0. The only fixed point or equilibrium solution to the linear dynamical system is 0. And now we want to check whether that's stable or not. And it might depend on the value of B. So let's take a case when B equals 1/2 and when B equals 2. I'm going to show the so-called cobweb solution. So let's draw a coordinate axis here. And I'm going to put two things on this. One is I'm going to draw the line y equals x for reasons you'll see shortly. So here's y equals x. And then I'm also going to draw the line y equals 0.5x because 0.5 is my constant that appears. So that's a line with positive slope but half the value. So it goes through points like this. And that's y equals 0.5x. Now, well, let's do something called cobwebbing. Suppose I start right here. Here's my a sub 0. When I plug that into the dynamical system, it says multiply that by b, in this case 0.5. So that would generate this value. And then that output becomes a sub, I started with a sub 0, then I generate a sub 1, and then a sub 1 immediately becomes the input for the next time I run the recurrence. So in other words, the output becomes the next input, or y becomes x. And so I run this value over here. And now it's a new problem to start right here. And so I plug that into the function, in other words, multiply by b, and I get here. And then that output becomes the next input, and I go here and down and so on. So I can put arrows on this path to show that the flow. I start here, I move, and so on. And the point being, I start somewhere near 0, and you can see the flow is taking me toward the origin. How about if we start over here? So here's another choice for a sub 0. I plug that into the function and get this value, run it over to y equals x, plug it into the function, make y equal x, plug it into the function, make y equal x. And again, you see that if I started with a negative value, I'm still getting run toward the origin. My limit in either case would be a equals 0. And so this is a case where the a bar equals 0 is a stable solution. Let's look at the other case. When b equals 2, I'll do the same thing. Graph the line y equals x. And graph the line y equals 2x. And now let's cobweb. And by the way, the name comes from the fact that this is sort of supposed to look like a spider web. Later on, we might see some different geometries where it becomes more apparent that the appearance is more like a spider web. So suppose we start, I'm going to start close to the origin this time. Suppose we start here. So what do? I plug it into the function. So I go up until I hit y equals 2x. Then I go over to y equals x. So I plugged into the function, got an output. Now I'm making my output the new input, plug it into the function, make the output the input, plug it into the function. And if I add tracing arrows on this, you see that I started here and the dynamical system is pushing me away from the origin. The values are getting bigger. So here would be A1, it's bigger, A2 is still larger. And similarly, if I start over here, for example, get my y value, y equals x, get my y value, y equals x. And again, I'm getting pushed away from the origin. So here's a case of instability. And I should say a bar equals 0 is stable. A bar equals 0 is unstable. So finally, find the solution. Let's match notation. This is a B. And find the solution. Well, we did a much harder case than this one already. If I just look at what happens here, x1 equals bx0, so x2 equals bx1 is b squared x0, so x3 is bx2 is b cubed x0, and so this one is easy to see that xn equals b to the n x0. And the question is, when does this approach 0? So this goes to 0 exactly when. So think about b to the n. If b is a number like 2, then as n goes 1, 2, 3, this gets larger. I don't go to 0. If b is negative 2, same thing. If b is positive 1, I don't go to 0. If b is negative 1, I don't go to 0. If b equals 0.5, 0.5 to higher and higher powers is getting smaller. And so what you discover is that this will approach 0 exactly when b is smaller than 1 in magnitude. And that was the case here in the first graph when b was 0.5, stable equilibrium point at 0. And it was not the case here when b equals 2, unstable equilibrium point at a equals 0. Okay, that should do this discussion. We'll stop there.